Okay, in this second example, and I think last video for Lab 7, I'm going to go over a three-way ANOVA with one replication. Now, that may raise some red flags for you. Why in the world would you run an experiment with one replication? And if that's how you reacted, I'm glad, because that is something that should cause you concern. I just want to talk about that a little bit. When we say there's one replication in a three-way ANOVA, what we're talking about is that there's only one experimental unit for every unique combination of all three factors. So for A1, B1, C1, we actually have only one experimental unit. But we do have replication in terms of all the two-way combinations of factors. A1, B1, for example, is going to appear at both levels of C. C has two levels. And so A1 and B1, that combination appears twice in the experiment. There is, in fact, replication. And it turns out that for every A-B combination, there's a replication of 2, because that's the number of levels of C we have. For every A-C combination, we have 5 reps in the experiment, 1 for each level of B. And for every B-C combination, we have 3 replications, for 1 for every level of A. So as it turns out, if you can run a factorial experiment with one rep when you start getting into 3-way, 4-way, and more factors. You can run it with one rep. The thing that you forfeit by doing so is any ability to include higher interaction terms in the model. And I'll show you that right here. So if this is the data set, I've loaded up the script here in RStudio and imported the data set, which I'm calling fact.dat. It's very creative, factorial.dat. And when we bring it in, what you'll see is that we have a data frame. A, B, and C all need to be reassigned as factors. And so here's our 3x5 factorial, 3x5x2 factorial. We have 30 observations in the data set. 3 times 5 times 2, we have 30 unique combinations of the 3 factors and 1 rep each. Now, if we run the ANOVA here, using A star, B star, C, that is shorthand. Here's the ANOVA table, the resulting ANOVA table. That is shorthand for A, B, and C, the main effects, all the 3 two-way interactions and the 3-way interaction. That's what the A star, B star, C is shorthand for. And when we run that, we see that we run out of residuals by the time we get to the error. This 3-way interaction ate up whatever degrees of freedom we had left over. And so we have nothing to test our hypotheses with, so we have no F values, no P values. So what we would have to do if we wanted to run this model is that we would have to include all 3 factors, but then cap it using the caret syntax, cap it at the 2-way interaction level. And if I run that, what you see is that the 3-way interaction is removed from the ANOVA, and those 8 degrees of freedom get assigned to the residual. So that's great. Those 8 degrees of freedom come from 2 times 4 times 1. So that cost me 8 degrees of freedom to put it there. And now I do have a mean square, and I do have degrees of freedom in the error to run all my F-tests. And what we see is that we have highly significant main effects across all 3 factors, and we have highly significant 2-way interactions for all of the factors involved. Now what we're doing here, this is similar when we have one replication in an RCBD where the block treatment interaction functions as our error. Our assumption is that the interaction is in fact non-significant, and that interaction term, therefore, is a good estimate of the true experimental error. And we're making a similar assumption here. We're assuming that that 3-way interaction is actually a good estimate of the experimental error, or that the 3-way interaction itself is non-significant. But unlike the RCBD case or the 2-factor case where we could use a 2-key 1 degree of freedom test to at least take a peek inside there and look at the quadratic component of that residual predicted relationship to see if indeed it is non-significant, we can't really do that here. But we can do a little more than just assuming things are non-significant, the 3-way interaction is non-significant. We can create a new response variable. And this is what I was doing in lecture today, talking about lecture today, is we create a new response variable that is no longer yield, for example, this y is no longer yield, we create a new variable that is the effect of C. Now, if you remember, C only had 2 levels, so it's quite easy to go through the data table. This is what we're showing here. It's quite easy to go through the data table and find those instances where A and B are the same. Remember, we had a replication level of 2 for all A-B combinations. So this combination of A1, B1 occurred twice in the data set. And so we can take those 2 values, subtract them, and what that's going to give us is the effect of C at that level of A and B, and we can get a number. I've created that new data set. This is Lab 7 Example 2B CSV. So let's pull that in. Let's pull that in. Let's go here. Right there. And I'm going to call that fact.dat now. And here you see we have A, B, and C. We have the Y. And now I have the C1 minus C2 column. And so for every combination, every unique combination of A and B, I have the effect of C at that level. Perfect. So now with that in there, I can now generate a 3-way interaction plot. I can't do any statistics on this. I can't run any f-tests or run an ANOVA on this. The reason being that I don't have any replication. I only have this one value at this level of A times B. But I can visualize it. And so here again, we're using the HH library and the interaction plot function. But now, instead of having the response Y being explained by the 2 factors I'm interested in, I have the effect of one of the factors as the response variable. So this C1 minus C2 effect is now explained by A. I'm grouping by B. Specify the data set. I'm turning on my error bars, which probably makes little sense in this case. And that's it. Set the range, set my offset, and let's see what that looks like. Object B not found. I re-imported my data set, but I didn't assign them as factors again. There we go. Now I have factors. Hold on a second. Let me start over here. I'm going to re-import my data set. Try again. Fact.dat. I don't think I specified a header. There we go. Import. It's there. Assign all my factors. Now let's go try this. And there we have it. Whereas we had very significant 2-way interactions in this data set, AB, AC, and BC, when we visualize the 3-way interaction, it's like seeing in 4 dimensions. You feel very powerful. But the waters have calmed. We have very nice, roughly parallel lines in this case. And as I was saying, even though we specified standard errors, no standard error bars show up here because we have no true reps anymore. We're just getting a sense of the overall shapes of the lines. And of course, we can visualize the other way around. Instead of putting A on the x-axis, we can put B on the x-axis. And in this case, we have 3 lines, 1 for each level of A. And the fact that the average of the blue line, the average of the pink line, and the average of the green line are different is telling us that C has a different effect depending on which level of A you're talking about. So this is what's underlying this significant CA interaction. And the same way, you can look at this plot, the fact that the average of the green line and the blue and yellow and pink and red are all different is telling you that the effect of C is different depending on the level of B. And that is this highly significant CB 2-way interaction. But when we pull it all together and we define our response variable as the effect of C, we get roughly parallel lines across all 3 levels of A. What that's saying is that the differential response to C across the levels of B stays relatively uniform across the levels of A. And so there is our non-significant 3-way interaction, which tells us, going back, that this is a relatively justifiable thing to do, that the three-way interaction does provide a reasonable approximation of the true experimental error. And so we can get away with an analysis of how three factors relate to one another, the dependencies or whether or not they're independent, using a single replication. And so this is one way you can keep the number of experimental units down in a factorial, even though you're adding more factors to the model, by forfeiting in some sense this ability to test statistically for these higher order interactions, although it is nice to try to visualize those things and to give yourself some confidence that indeed they were non-significant or are non-significant. And I think with that, that is all that I go over in Lab 7. That's about it. So the next homework is posted. It follows this homework and the lectures obviously very closely from this week. And good luck, everybody.